Okay, so let's talk a little bit about how fetal hemoglobin is able to have a higher affinity for oxygen than adult hemoglobin, and thereby how the fetus is able to actually get its oxygen from the mom without being exposed to air. So let's talk about 2,3-BPG first. Sometimes you might see it written as 2,3-DPG. So this stands for 2,3 bisphosphoglycerate. Or the DPG would stand for 2,3-diphosphoglycerate. Okay, and this is a really special molecule because it is an allosteric effector of hemoglobin. Okay, so allosteric effector. Okay. Allosteric effector. Okay, so here's the structure of 2,3-BPG. And what you'll notice about it is that it has a very high negative charge. So it has 1, 2, 3, 4, 5 negative charges. So its overall negative charge is -5. That's really negatively charged. So this means that it's going to want to bind to something that's quite positive. It'll bind to something that's positive with more affinity than something that is neutral or more negatively charged or even less positively charged. Okay, so 2,3-BPG's role is it stabilizes, okay, so 2,3-BPG, okay, it will stabilize that T state, okay, of hemoglobin. So when hemoglobin is oxygenated, I'm just going to draw this here. So let's say hemoglobin has 4 subunits, okay? Put alpha here, alpha, beta, and beta. So hemoglobin has 4 subunits. It's got 2 alpha and 2 beta subunits. When it is bound to oxygen, we'll say O2, 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 and O2. This is considered the R state. So the R state. Well, hemoglobin, what it does is it stabilizes the T state. So once one oxygen gets offloaded into respiring tissues, that 2,3-BPG is going to come in. BPG will come in and it'll bind to the middle of the hemoglobin molecule. And it'll further promote the release of the remaining oxygen. Okay, so promotes release of remaining O2. Okay. Okay. So how exactly is this different between an adult hemoglobin and fetal hemoglobin? Well, let's take a look at the structures that are different. Okay, so you'll notice that in adult hemoglobin, we actually have 2 beta subunits, while in fetal hemoglobin, we have 2 gamma subunits, okay? So the beta subunits here have what's called a histidine. So histidine 143 in that specific spot. In fetal hemoglobin, that histidine has been substituted to a serine. Okay, so serine 143 in that same location. So we know that histidine is a positively charged amino acid, okay? So positive, and serine is neutral, so I'll just say neutral. It's a neutral charge. So if you remember that our 2,3-BPG molecule is super negatively charged, it's going to want to bind to that adult hemoglobin with higher affinity, okay? It's going to bind really strongly to that adult hemoglobin, thereby promoting the release of oxygen. Whereas 2,3-BPG is not going to want to bind to fetal hemoglobin because it does not have as strong of a positive charge, okay? So when 2,3-BPG tries to come in, it's going to bind really strongly to adult hemoglobin. Right in the middle there. Okay, so let's take a look at how this affects our hemoglobin binding curves. Okay, so you can see, so partial pressure at the bottom here of oxygen and hemoglobin oxygen saturation over here. So the fetal hemoglobin curve is left shifted because it has a higher affinity for oxygen due to the lack of 2,3-BPG binding. So 2,3-BPG stabilizes the T state. In other words, it decreases the affinity of hemoglobin for O2, right? But it doesn't affect fetal hemoglobin because, as I mentioned, it is neutrally charged. It doesn't want to bind to fetal hemoglobin as much. So when we're looking at this curve here, let's take a look at the P50s here, okay? We'll use orange. So let's say somewhere here, P50, probably going to be over here for adult hemoglobin. And this should be somewhere around PO2 27. Okay, and that's defined as the point at which half of your hemoglobin is saturated with oxygen for the adult hemoglobin. Well, for fetal hemoglobin, at that same partial pressure, we can see it's much more saturated. So we'll take that same partial pressure of 27 and move up. And this would probably be around a 75 to 80% saturation. 50. So we'll say this is probably around 80% saturation. Okay, so that fetal hemoglobin can basically be a lot more saturated at a lower partial pressure of oxygen. And the P50 for fetal hemoglobin is actually around 20 for fetal hemoglobin, okay? So, in summary, how fetal hemoglobin is able to have a higher affinity for oxygen and thereby the fetus able to get oxygen from its mom without being exposed to air is due to this change in the subunits of the hemoglobin that it has. So it's got these gamma subunits, and the key to that is a change from histidine to serine, thereby making it harder for 2,3-BPG to bind.